So, yep. Cool. Software complexity. Okay. This lecture will follow another way of explaining it. So normally we explain what is it, why it is important, and then how, right? But this time we'll do another way. Like we will first explain how, okay, and then we'll move on to what is it, okay. But anyway, we'll start with why. Okay, so we need to have a motivation to learn this concept, to learn this lecture, right? So why do we care about software complexity? Like software is complex, so you may have already realized in your major project, there are a lot of influence factors, right? Your code, and also your runner, the prototype, your group members, the deadlines and everything. So all the influence factors, they influence the software complexity. But here, we want to minimize the complexity because we want to reduce the cost. We want to deliver our software as early as possible because we have other competitors in the market who may be working on similar softwares, okay, and we also want to estimate like the cost of the time so that we can plan ahead or ask for budget from the investors or others. So now, how can we measure the software complexity? And then we'll come back to what. Okay, the first one is called cyclomatic complexity. Okay, so when we talk about test coverage, remembering that there was one measurement called branch coverage. Okay, and I think Hayden should also have mentioned that branch coverage is important because there are, for example, in a if-else cases. So there's an if and there's an else, and we need to test both cases. Okay. So in these branches, like for example, if and else statements, they kind of introduce complexity to your code because there are two different routes that may happen during the code execution. And this cyclomatic complexity is to measure the branching complexity of the functions. Same with the term branch in code coverage. So the branch here has nothing to do with the Git branch. It's the branch of your conditional statements. So in your if-else statement, so conditional or while loop. So this is the branch that we mean here. And this cyclomatic complexity is to measure the branching complexity of functions. Okay. And this cyclomatic complexity, it measures by counting the number of linearly independent paths in a function. Okay, what is this? What is this linearly independent path? We are talking about something in the individual project. And okay, the linearly independent. So what is linear? So for example, A equals to 2. B equals to 3, so these are linear. And what is non-linear? So linearly independent is if and else because they are separate role, separate branch, and maybe there's also loop. Okay, so we are interested in these non-linear branches. Okay, we'll come back to this formula. So how can we calculate this cyclomatic complexity? We first need to convert our function into a control flow graph. Okay, we'll see examples of this graph. And then after we got this graph, we can calculate the value using a formula given here. So here are some examples of how we can convert our functions into graph. Okay, so let's have a look at this first one. So this is an like if-else statement. So if expression 1, then we conduct statement 2. Otherwise, we conduct statement 3, and if statement 4. So here statement 4 is the ending point, and we start with this if statement, like if expression 1, if it's true, then we move on to statement 2. Can you see here? Yeah, okay. And otherwise, we move on to statement 3, and then we end up with and here like statement 4. So in a graph, it looks like this. So this is a graph of graph demonstration of this if-else statement. Okay, so here N1, N2, N3, and N4, they are the nodes in this graph. And we also have a couple of ages. So here's one age, okay, the other age, and age. Okay, so here's the concept of node and age. Let's have a look at the second example, switch. So we have a couple of cases, case 1, case 2, and case 3. Okay, and the graph will be looking like this. So we start with N1. For case 1, we move on to statement 2, and otherwise N3 or N4, and we end up at N5. We may also see some loop, like while loop. Okay, so we start with N1, and under some conditions, we move on to N2 and then go back to N1. And in some other cases, like we end this loop and end in N3. Okay, so this is examples of graph, and the concept here is node and age. And then we can come back to this formula. So now we can calculate the cyclomatic complexity using the number of ages minus the number of nodes plus 2. So you can see that in this formula, we only consider the non-linear branches. So we are not considering at all the linear ones. Okay, so this is cyclomatic complexity. So let's see more examples. Okay, so here's a function called for. If A, then B, else C, and end up together, like maybe have another function or return afterwards here. So we can see that if A is true, and then we move on to B. If it's false, there's another branch, and we go to C. Okay, and then maybe we return a D. Okay, and the cyclomatic complexity here is the number of, what is it? The number of ages minus the number of nodes. Age is 1, 2, 3, 4. 4 ages minus the number of nodes, which is 4, plus 2. So the cyclomatic complexity equals to 2. Yeah, question?
The graph is like, there's no if else, it's just one line. Then it will be just one.
It's 0. So for example, if you have a function, which is in this function, we only have A equals to 2. Then the cyclomatic complexity is 0. Because cyclomatic complexity only consider the linearly independent branches. So for the linear ones, this cyclomatic complexity doesn't consider that at all. So this is actually one of the drawbacks of cyclomatic complexity. So if there isn't any branches in your function, then we just assume this complexity is 0. So no matter how many linear statements are there in the function, it would still consider the complexity as 0. So this is actually one of the drawbacks of cyclomatic complexity.
What do you mean by branches?
Branches. Okay, so
Is it like if else?
yes. Yes.
So there's no if else, then it's 0 because there's
Yes. If else or while loop, or the example we have seen here about the switch, but we may not use that much about switch in this course. Yeah. So these are non-linear ones.
So essentially there's no if else or while loop. and your nodes are just like one line. Essentially, its complexity is just 0 because there's no
cyclomatic complexity is 0. So there are multiple ways of calculating complexity, and cyclomatic complexity is one popular one, like quite popularly used in industry. Okay. So this cyclomatic complexity is actually originally designed for calculating the testing complexity. So in the testing, you may have noticed that if you have a lot of if-else statement, you need to have a lot of different test cases, right? So cyclomatic complexity is powerful for estimating your testing complexity. Right. So, and testing is important in software engineering, right? In software designs. So this is why cyclomatic complexity is popular in software industry. Yeah. Okay, so this is the first example, a very straightforward if-else statement in this function for. Here's another example. So in this else statement, we have another if statement. Okay, so you can see that in C here, we have a separate branch which goes to D, but still end up with E, like we return something, right? So we start with A, and there are two branches here which goes to A, the other goes to, we start with A, and if it's true, we go to B statement, otherwise we move on to C, and if C is true, and then we go to D statement, otherwise we end up here at E. So this is another example. And we can calculate its cyclomatic complexity here. It's the number of it's the number of edges minus the number of nodes plus 2, and then its complexity is 3. Okay, any questions so far? Let me have a look at online. All good. Okay. Have a look at another example. So here's the example for while loop. Okay. While A, then B. Otherwise, C. Okay. So here's a loop between A and B. So if A is true, then we move to B, otherwise C. And here's a loop here. So the number of edges is 3, the number of nodes is 3 plus 2, and then we end up with cyclomatic complexity is 2. One more example here, a little bit more complex. How can I explain this? So we have already seen this example before, right? In your tutorial and also in our lecture. So this is the function day to year. So given a day from the first day of year 1970, and we want to know which year this date is in. Do you remember this function? Yep? Nope? Okay. Okay, so let's have a look at the graph from this function. So while this is greater than 365, so here we start from here. So remembering that we ignore all the linear ones. So we start from the while loop. Okay. So while this is greater than 365, if it's false, then we just return year, right? We directly come back to the end here. And if it is true, okay, we move on to here. And is leap year is true. So if is leap year is true, okay, and then we move on to another if question here. So if this is greater than 366 here, I think I'd better draw somewhere so that can be easier to understand. I didn't bring my iPad today. How can I draw somewhere? Sure. Okay, I'll try to explain. So here, this node here is this is greater than 365. Okay, so this edge is straightforward, right? If this is not greater than 365, we return year. So this is a straightforward one. All right. If this well, so if here is true, then we move on to here. So this node here, and they will face another if-else statement. Okay. So if here is false, it will move on to this one. So here, and then go back to this while loop. Okay, and if each leap year is true, we move on to another if statement, move on to here. Okay, and if this new if statement is false, and go back to this while loop. Otherwise, this minus 366 year plus 1, and go back to this while loop. You need some time to digest. Think about that. I will leave this page here. Got any question? I should have a pen. So here is the statement, days is greater than 365, so we start here. Okay, so if this statement is false, we move to here, return year, this statement. Otherwise, we move on to this if-else statement here. Okay, and if each leap year is false, we move to the else statement here, and we go back to the beginning point of this while loop. Okay, if this if leap year is true, we move to this node, and then another new if statement. If this is greater than 366, okay, if it is true, we run this statement and go back to the initial point of this while loop. Otherwise, go back to the initial point of while loop directly. Make sense? Yep. Okay, so now we can calculate the number of the ages minus the number of the nodes plus 2. And we can see that this function day to year, the complexity is 4. All good? Okay, so you may think, wow, this function, this day to year function is too complex. Okay, so we have while loop, and inside this while loop, we have if-else statement, and inside of one of the if statement, we have another if statement. So you may think, well, this is too complex. Okay, so you can think, well, now we need to write the test cases for this function. We need to write a lot of test cases, right? So to make sure the branch coverage is good enough in your test coverage, right? So we may want to reduce this complexity and still achieve the function. So now we have another new day to year function, and they are doing the same thing, but it's more like smarter in the way that the complexity is reduced. You can compare these two, like in the second example, we start with if this is greater than 0. And in the previous example, we start with if this is greater than 365. And then if, in this case, we have one more else statement. But in this example, we kind of removed one of the else statement. So the complexity is reduced. So we talk about like good design of our code. And here we are adding more criteria of what is good design of our code. is to have less complexity in our code, like smarter, better design, but they are achieving the same goal. They are doing the same thing. And you can see that we have less complexity, like less node, less edges, and we end up with the cyclomatic complexity is 3. And in the previous example, the complexity is 4. So this is how we design better code with reduced complexity. And then we can have less test cases. Right? So some people argue that 10 should be the maximum cyclomatic complexity of a function, but some argue 8 would be also fine. So it has some drawbacks of using cyclomatic complexity. One of the drawbacks is that we just mentioned about like we kind of ignore all the linear statement. So even though we have a function with like hundreds of lines, but none of those has any branches. None of them have a conditional statement. So we kind of think that complexity is 0, which is not true. Right? There still should be some complexity. So this is one of the drawbacks of using cyclomatic complexity. And also, sometimes we want to reduce this cyclomatic complexity that we separate two functions so that each function have lower complexity. However, sometimes separating those functions doesn't make sense. It's going to make our code harder to read, harder to understand, harder to maintain. It's just for like reducing the complexity. So sometimes force us like not designing a better code. So these are the drawbacks. But it's still popular in the software world is because like it matches quite good with the complexity of testing. Okay. So cyclomatic complexity was originally designed to indicate a program's testability and understandability. So this is its original purpose, its original goal. Depending on the programming language, so for some programming language, so sometimes we have tools that exist that we can use directly to calculate the cyclomatic complexity. So this is one like pros of cyclomatic complexity as well. So there are also another two popular metrics of software complexity. So one is called cohesion and the other one is called coupling. Have you heard about those two terms before? Cohesion and coupling? Nope. Okay. So they are also for measuring the complexity, and they are contrast with each other. Okay. So cohesion measures the degree to which elements of a module belong together. Okay, so we want to have related modules close to each other. So for example, if you want to separate a function for low cyclomatic complexity, it kind of you are separating two related parts. So we want to have high cohesion, meaning that related elements are kept close to each other. Okay. So it is usually expressed as low or high, so we say high cohesion or low cohesion. And high cohesion is good, meaning that related components or modules, they are close to each other. And on the opposite is this coupling. Coupling is a measure of how independent different modules of each other. So we want to have independent modules separate. So if we have two components in our code, they are irrelevant. We do not want them to be dependent on each other. Okay, so this is also relevant to the maintainability of our software. So when we talk about maintainability, we mentioned that if we change one part of a code, we do not want this change to influence other part of your code, right? So we want to make sure independent, different modules are separate from each other. So we say loose coupling is good. So the coupling is described using loose or tight. Okay, so cohesion is described with low or high, and coupling is described with loose or tight. Okay, so tight coupling occurs when one module modifies or relies on the internal working of another module. So tight coupling. So if you have tight coupling in your code, it means that when you change one part of your code, it will influence another part of your code. So they are dependent on each other. So we have a lot of dependencies in your code. We say tight coupling. So if we separate independent code, like we want to make sure they are not influencing each other, so we say have loose coupling, and the loose coupling is good. An example is that web applications, so we aim to have applications that their front end and their back end are loosely coupled. So we do not want to, like we added one of the buttons in the front end and we need to change a lot in our back end. So we do not want that to happen, right? So we want to have loosely coupled front end and back end development. Okay. So coupling and cohesion are another two complexity measurements in addition to the cyclomatic complexity. But we are not covering too much about how we calculate exactly the coupling and cohesion complexity here in this course. Okay, so now we've talked about how, then now we are coming back to what is software complexity. So this is the only lecture that in this course like we talk about how first and what next. So the reason is because, so now we have learned about how. You may be wondering like how we can reduce this complexity. So we have seen the example of day to year, so that example. So we are reducing the cyclomatic complexity a little bit, but in the overall, like for large software like Netflix or YouTube or whatever, so we can start from the bottom. So we can start editing, modifying from the bottom, like the functions, the code, and the pieces by pieces, and we reduce the complexity. However, in the software, there's not only the functions, but there are a lot of influence factors. And during the software development process, there are a lot of influence factors. One example is we kind of have constraints, like the constraints from our hardware, right? Maybe also from regulations or legal constraints in specific domains. Okay, so we also have seen in the major projects that sometimes we are also constrained by the runner or whatever. So, and also the people in the project are also influencing factors. So there's a very influential book or article is called No Silver Bullet. So there's no silver bullet of how we can exactly reduce the software complexity. Okay, so they discuss this software complexity comparing with the complexity of in other domains, in other industries other than software. So for example, in manufacturing, so for example, a company who are making shoes, right? Who are making shoes. So if you want to have more shoes produced in a shorter time, what are you going to do? Recruit more people, right? So you can have more people so that you can have more shoes produced in a less time. Is that the same case in software development? It's not true, right? It's not the same. So imagine your project. So you are now in iteration 3, and you want to have your project finished earlier with better quality. And we, like the code said, we are adding 2 more people to your group. Can you make sure that your project can be finished earlier with better quality? Not exactly, right? Because they will take time to read your code. Okay, so they also need to learn how to work well within your group. Okay, so this is also why some, not many, but a couple of our groups in this course, they have only 3 members, but they can even outperform than some of the groups with 6 group members. So it's very complex. There's no silver bullet, like how many people in a group we can perform the best. So there's no silver bullet. So there are a lot of influence factors. So adding manpower to a lead software cannot really help make our project or the product delivered earlier. Okay. So there are two different types of complexity that defined by Brooks. One is called essential, and the other one is called accidental. So essential complexity, for example, you are designing a car, right? Some essential features or essential complexity are introduced. For example, your car needs to have wheels, right? They need to have wheels, they need to have engine, and they need to have seats. So these are essential, right? So these are the complexity that you cannot remove at all. Right, so you need to have a car that can actually work. So similarly for software, for example, if you have a to-do tool, like for to-do items, you need to have somewhere that can host your to-do list. Okay, otherwise it's not a to-do tool, right? What is accidental complexity, or what is accidental features? Coming back to the example about the car, right? You may have V6 or V8 engine, right? If you do not have a V8 engine, at least your car can move, right? With your wheels, with your engine, like no matter what engine it is, and with the seats, right? So, but whether it's V6 or V8, this is accidental. You want to have a better one, right? So maybe introduce another complexity factor. Okay. In the software context, examples can be like how you are using your data, like whether you are generating or passing data in specific formats, like whether you are using JSON or CSV or like other formats to storing your data. So these are accidental complexities. Essential or complexity are fundamental that cannot be removed. Like we cannot remove the wheels of your car to reduce the complexity, right? But accidental complexity sometimes can be migrated. Okay, maybe we can use some smart libraries, smart use of libraries. For example, we want to calculate the date of year. You may not need to write the code from scratch yourself. Okay, you may use a library from NPM. Right? Smart use of this library can reduce the complexity of your tool. You have less lines of a code, right? Because you're just calling the library. And you may also follow some standard. So you are not being too creative, being too smart in your code, that you are writing something that others cannot understand or cannot follow. So this can introduce this accidental complexity. But if you are follow the standards, you are doing in the way like everybody is working in that way, so it kind of remove or reduce that kind of accidental complexity. However, it is still hard to remove entirely. Okay. So why we say it cannot be removed complex, and sometimes the accidental complexity is somehow what differentiate our good software engineers from the regular or average software engineer. Because for like regular or like average software engineer, we know how to code, right? We know how to write the functions. But good software engineers, they know how to incorporate with different environmental factors. Because, for example, they know when there are some constraints from the hardware or there are some constraints from the people, they know still how to manage their software properly. So they still can have a good performance in their software. So this is actually how differentiated us as a good software engineer. So in the modern software systems, here are 4 types of complexity that are mainly coming from like accidental complexity, but they are also important and cannot avoid in real-world software industry. For example, the first one, complexity. So complexity of complexity. So here it means that software development process itself is complex by nature. So you have done like iteration 0 to iteration 3 now, so you can feel that it's complex by nature. Alright, so you need, for example, when you write the test cases, there are a lot of edge cases that you need to think, you need to discuss with your team members. And also in the real world, we need to like maybe conceptualize the real world problem into our algorithms, into our functions. So it's complex by nature. The next one is conformity. So adding to its inherent complexity, additional complexity may arise from the fact that software cannot be created in isolation. Okay, so it needs to be built on some kind of like pre-existing software, or like there will be also constraints from the hardware, or there may be some real-world constraints, or there may be some government regulations, like legal factors that can limit the extent to which complexity can be reduced. So this is conformity and changeability. So we talk about changes or changing in software design process quite a lot in this course. So the change may come from like the stakeholders. They change their mind. So they originally said they want to do this and that, and then later in the development process they changed their mind. Or maybe because you develop a very popular tool, a very popular software, and a lot of people starting to use your software, and it's quite common that they may use your software in a different way, that you need to have different features for them. So for example, originally you only want to have a to-do app that you can add and delete to-do items. Maybe later you want to have like a deadline set to each of the to-do items. You may want to have other features. So you are always changing your software. So changeability also introduce more complexity in your software design process. And the last one is called invisibility. So what is invisibility here? So for example, if you are designing a cup, right? So you can get some papers, roll them somehow, and you can draw something on the paper. You can like have a prototype that you can see directly, right? And you can add it like what size it can be, what color your cup can be. You can also draw something on it, so it's visible. However, our software is invisible. We try our best to make it visible by using some prototypes and other, but it's still something that we cannot touch. It's still invisible. So this invisibility also adds to the complexity of our software design process. So now let's come back to here. So software engineering knowledge. I heard the saying that like the technology world is emerging so fast. So for example, now we are using JavaScript, but like a couple of years ago or many years ago, people may only use C or other programming language. Right, and now we have GPT, and in the future we may have a new programming language. Right, the technology world is always emerging and changing so fast. So you may think, well, I learned JavaScript today. What about in 10 years? Am I still be using JavaScript? Will that be still sufficient? The answer may be no. So you need to always be learning. So you're always learning new programming language. You need to be up to date with the technology. So for example, the pipeline, right? And also tools that are emerging. So we are always learning. So the coding knowledge or technology related knowledge. So why we are learning this? So this knowledge may also be useful in a couple of years. We need to learn new coding language in the future. So this is so this may be only half, at most half of what we are actually learning here in the universities. So more importantly, we are learning about how we can tackle the accidental complexity. Right? Essential complexity is maybe just the coding, programming, but accidental complexity is what differentiates us from other average software engineers. So we know how to tackle those constraints, like how do we manage changeabilities, how do we manage invisibility or conformity, like that. So the conclusion here is that there's no silver bullet how we reduce the complexity. Okay, we can try to reduce the complexity by better design of our code, as the day-to-year example has shown us. But there's no silver bullet like how we can exactly reduce the complexity to like a good extent. Okay. And here are the open questions that there isn't really an answer to it. So for example, the first one, is there a concrete process for distinguishing accidental and essential complexity? What do you think? It's a hard question, right? So there's no single answer to it. And the next one is, how much of complexity of modern software is accidental? I don't know. It really depends. Sometimes I think the accidental complexity is greater than the essential complexity. Right. And the next one is, to what degree will accidental complexity be removed in the future? Oh, well, I think this is impossible. Right, this cannot be removed at all. Yeah, so we provide more further reading in the slide, including the original no silver bullet paper. This is a quite interesting article to read. Some more modern descriptions of the no silver bullet. There's a link, and also there's a rebuttal of that original paper. So that paper was actually published in 1987. So it was quite long ago. And most of the problem that has been raised in the original paper in 1987 is still the case nowadays. So let alone we have new programming language, we have new tools, we have AI, but most of the complexity issue still remains, no matter what kind of tool that we have got. Okay, great. So this is today's 2 lectures. I'm not going to show you this QR code because we have the max experience review now. So if you have time now, I will encourage you to take about 3 minutes to fill in this survey. So if you do not have any comments, at least like tick some boxes will be very helpful as well. Any questions? All good? Yeah? Cool. Great. Yeah, that's all for today. Thank you, everyone. And next, on Friday, we will talk about the very last lecture about Git undo. And we also, I will try to mention a little bit about the individual project.